Today I'm going to present to you the E.A. Wood, Elizabeth A. Wood Award winner for 2014, Dan Rabinovich. And just to remind you a little bit about what the Elizabeth A. Wood Award, Science Writing Award is. The award is named in honor of Elizabeth A. Wood, president of the ACA in 1957. And she is the author of science books for lay readers. You'll remember Science for Airplane Passengers. Persons who have written books or articles that bring science to the attention of a wider audience are eligible, and they need not be crystallographers or scientists, but writing, including artistic efforts, museum displays, and stamps are included, because that's what our current winner will be talking to us about. Let me just tell you a bit about Dan Rabinovich. He was born and raised in Lima, Peru, graduated from Catholic University in Peru, and with a BS in chemistry, and then moved to New York for graduate school at Columbia. He's a professor of chemistry at the University of North Carolina at Charlotte. And among his research interests, which are synthetic and structural inorganic, bioinorganic, and organometallic chemistry, are collecting stamps, international stamps, France, Britain, Peru, Sweden, Switzerland, and perhaps we will hear of some others, in particular commemorating the International Year of Crystallography. About Dan Rabinovich. He was born and raised in Lima, Peru, graduated from Catholic University in Peru, and with a BS in chemistry, and then moved to New York for graduate school at Columbia. He's a professor of chemistry at the University of North Carolina at Charlotte, and among his research interests, which are synthetic and structural inorganic, bioinorganic, and organometallic chemistry, are collecting stamps, international stamps, France, Britain, Peru, Sweden, Switzerland, and perhaps we will hear of some others, in particular commemorating the International Year of Crystallography. And this is the award. Small token of appreciation. Yeah.
Well, thank you for the nice, generous introduction. It's an honor and it's a pleasure to be here. I think it's a wonderful opportunity, especially in the International Year of Crystallography, to talk about my two passions, stamps and science, and how I have been using both in my teaching, in my writing for a number of years. So I'll really start from the beginning. And so a long time ago, back all the way up to the 1830s, right? It was whomever received a letter had to pay for the letter. So they didn't think that was very, very fair. There was no connection with the size of the package or the letter, with the distance it had to travel. And so that was the status quo until around 1840. In 1840, Rosalind Franklin basically invented postage stamps as a way of prepaying for postage. It was a more reasonable, a more fair way of doing that. And so maybe you've heard of the penny black. That was the first stamp ever made. And stamp collecting started shortly after that. Within months, people started collecting stamps. And that word, philately, that people use sometimes for stamp collection, reminds us of the origin of stamps. It was the law to be exempt from tax, which was, of course, what the recipient of the letter was happy to acknowledge. And in more reasonable, more modern terms, philately or stamp collecting is the really collection or study of postage stamps and other postal matter as a hobby, or as I tell my wife, an investment. But maybe I shouldn't say that because my wife is here in the audience, so that's dangerous, but that's how it goes. And so stamps are really designed to send packages and letters. They don't stamps from all over the world that just are pretty and really have a message. A number of stamps, though, have a message. They have a contents, they have commemorate an event. It could be the Wright brothers, it could be Buckminster Fuller, it could be Ukichiro Nakaya, this Japanese scientist who studied snow crystals for 30 years, and got to be on a postage stamp. And the key is, of course, that this is a very attractive, a very effective way of illustrating oral presentations, papers, and not only that, it's actually a very inexpensive way to do it. Now there's Google Images, you can really get all these images and really use them as I do in my teaching and my writing. So it is always, even for the younger generations who maybe don't use a lot of stamps, don't go to the post office a lot anymore, but they know what stamps are. And you will see examples of stamps that have some crazy, interesting science. And this is a topic for starting a discussion in the classroom, and you'll see lots of examples of those. I've used these extensively in my teaching of chemistry. These are just some stamps related to chemistry. And, but of course, the topic today is crystallography. I have branched from chemistry into physics, into the metric system, things we always teach. But here is crystallography. And so we'll really start from the first reference to crystals. So Pliny the Elder was really the first one to describe in detail minerals and gemstones, some systematic approach in this Naturalis Historia, the first really encyclopedia of everything that was known at that time. We're talking about 2,000 years ago. And so the process, of course, in terms of crystals, and we are like crystals of crystallizing sugar from sugar cane or salt from brine, was also known in India and China for many, many centuries. And so that's kind of the beauty of crystals. And many of us, I think maybe a majority of us here, got into science because of the beauty of crystals. And so that is really important. And so during the Roman Empire, the art of tessellation became very popular, and that's an interesting, important concept, of course, in crystallography. These are mosaics from the 2nd century AD that show these repeating patterns. And that's really, of course, important in crystallography. And this is a section that I call crystals before crystallography. So these are minerals, gemstones, snowflakes, and this is how we can get really not only interested in crystallography, but how we can get other people interested in crystallography. And so there are lots of stamps that show minerals, samples of minerals, beautiful samples of minerals, as you can see in these stamps here. These stamps from China also show the names of some minerals, the formulas. That's when they are really informative, so you learn about the names, cinnabar, wolframite, some of these minerals. These are stamps from Turkey, again, formulas, names of some minerals. These are all stamps from Greece that also show minerals, as I show here. Pakistan, gemstones, there's many, many different stamps. This is just a sample of some of the stamps that show minerals. This is pretty cool. This is a set of stamps from Ukraine. But these were printed in a sheet of 6 stamps. Each stamp is an equilateral triangle. And of course, this one ends up being upside down. And of course, 6 equilateral triangles will make this hexagon. So it's a pretty cool way of printing these stamps with minerals. These are some of my favorites, not only for the Peruvian connection, but because they show the names and formulas of some minerals, but they show all the unit cell parameters for these minerals. And so it's fairly small, hard to see, but zinc sulfide is cubic, right? And so you'll see the correct cell parameters for the crystal, and that's pretty incredible for postage stamps. And you can collect a specific mineral or gemstone that you like. And so it could be quartz on stamps, it could be be rubies, it could be sapphires. There's lots of interesting stamps related to minerals. Now we'll jump forward now to Kepler. Now Kepler is really best known as a mathematician, an astronomer, and there's a number of stamps with Kepler, but it turns out that in 1611 he provided the first systematic description of snowflakes. By systematic I mean the first description where he talked about the hexagonal symmetry of snowflakes, where he made observations regarding the packing of spheres, and this is a really, really important concept in the development of crystallography. This is a small pamphlet that he wrote as a gift to the king at that time, and it's called On the Six-Cornered Snowflake. You can buy, I think, for $6 or $8 copies of this book, not the original one, on Amazon. And it's there on some Six-Cornered Snowflake. Really, really nice little book. And a few years later, in 1619, he had another book, Harmonices Mundi, where he talked also about geometrical forms, physical phenomena. So he was also interested in the mathematical relationship of crystals, and sometimes the relationship between crystals and planets. There's really interesting stuff with Kepler. Snowflakes on stamps. Lots of pretty stamps that show snowflakes, stamps from the US, from Sweden, from Spain, lots of different countries that show stamps with snowflakes. And again, fast forward to the late 1780s, 1790, when Hauy is a French mineralogist who really established the geometrical law of crystallization, the crystal growth associated, and there's a law that now is associated with his name. Sometimes he's referred as the father of modern crystallography. Now, this is a picture from from his paper, and that's how he explained little cubes, right, drawn in 3 dimensions, will make the shapes of larger crystals. That's the bottom, basically how he explained crystal growth. And a very similar picture, like this sort of extended cube, appears on this cover. A pretty rare cover is a cover from the 3rd International Congress of Crystallography in Paris, 1954. And here in the corner, you see this is more like a pyramid, but it's the same sort of drawing from Haui's publications. That's from 1954. The cancellation also shows a really nice pentagonal dodecahedron. So that's another really nice cancellation. And he appears also on this stamp from the Democratic Republic of the Congo. Don't ask me why. But Hauy appears not on a French stamp, but there he is on the Congo, so I'll take him into the collection. And Fedorov was also a fairly well-known mathematician and crystallographer who really came up in 1891 with an almost complete list of space groups. And so he did that. Well, first of all, I'll show you Fedorov is here. And in 2003, for the 150th anniversary of his birth, there was this stamped envelope prepared in Russia. So that's Fedorov. And I was saying that Fedorov, the development of space groups in 1891, almost at the same time but independently of Schoenflies. And so it's also 1891. There was an exact match between the two lists. There was a space group that was a duplicate, a couple were missing, but they started communicating with each other, and within a few years they came up with a final list of 230 space groups as we know it today. So that was Fedorov and Schoenflies, 1891. And so then we go, of course, to the birth of X-rays. We've all heard about Röntgen and the birth of X-rays, but it's a fascinating history, really, how X-rays came about and how they became really known. So this is really the oldest stamp that shows Röntgen. It's a stamp from Germany, 1951, It was the 50th anniversary of his Nobel Prize. The first Nobel Prize in physics was awarded to Röntgen. He appears on a number of stamps from many different countries, some of which, of course, have no connection with him. They just honor the Nobel Prize in physics, or maybe the first Nobel Prize in physics, the discovery of X-rays. So you see stamps from South Korea, from Suriname, Finland, from Macedonia, from Cuba, all over the world with Röntgen. These are small souvenir sheets that were also prepared. This first one is from Sierra Leone. Again, I don't really know why, but Sierra Leone, 1995. That was the centennial, of course, of the discovery of X-rays. And this one from Guinea was issued, in fact, a year later, in 2002. They were really supposed to celebrate the centennial of the Nobel Prize, but they were even a year late. That's the way it goes. This is a stamped card, a postcard with a stamp already that was prepared, issued in Poland, 1895, again the centennial of the discovery of X-rays. This is from Cabo Verde in Africa, another unusual item that again celebrates the centennial of the discovery of X-rays. And the Röntgen Museum, there is a Röntgen Museum in Germany. That's the house where he was born. And so there was this postcard with a stamp that shows the Röntgen Museum. This was prepared in Germany in 1974. It's a nice item for the collection. All right, so talking about the history of X-rays. So everything really started on, well, a few weeks, I would say, before December 22nd, 1895. And so what I show here is that first X-ray radiograph. You've seen the picture, it's everywhere in textbooks and everything. And you recognize that this is the first X-ray radiograph. It's the hand of Röntgen's wife, right? Anna Bertha came to the lab after a few weeks. He had been working, and so he asked her to be a volunteer. And so that's the first X-ray radiograph. I think shortly afterwards, of course, he developed this radiograph. She saw the picture, and reportedly, she claimed that she had seen her death with this picture. And that same picture appears on this first day cover from Germany, that is also celebrating the centennial of the discovery of X-rays. Appears on this stamped envelope from Russia. Again, wherever you see a hand, often associated with Röntgen, it's probably that. And the first publication came only 6 days later. This is amazing, right? So December 22nd, he was getting the first X-ray radiograph. 6 days later, including Christmas, right? And, he was, publishing this work. Short paper submitted to the Würzburg Physical and Medical Society. In 6 days, that's amazing, right? And so January 1st, this is really, really incredible, including New Year's Eve, right? January 1st, he sent samples of radiographs. He made lots and lots of radiographs, additional radiographs, and preprints of his paper to 90 of the top physicists all over Europe. Very, very sharp move, right? And this is incredible, because we're talking about 3 days, December 28th to January 1st. This is before Facebook, before photocopying, before any of that, right? No PDFs. And in 3 days, he had 90 copies of the paper, all these radiographs, all originals, of course, were distributed all over Europe. This is before the Nobel Prize. I'm almost not surprised that he got the first Nobel Prize with that kind of campaign, right? But it was really incredible. And so in a very short period, right, 4 days later, January 5th, this was already mentioned in the Die Presse in Vienna, eine sensationale Entdeckung, right? A sensational discovery. That's how it was promoted just 4 days later. January 6th, it was in Frankfurt, in London, the Daily Chronicle. January 13th, Le Matin in Paris. And good news travel fast. January 13th, this is just a couple of weeks, within a couple of weeks, he was invited to give a demonstration of X-rays to the emperor, to Kaiser Wilhelm II in Potsdam, which was a huge deal, right? Just 2 weeks after the paper was submitted. January 16th, it appears on the New York Times. January 20th, less than 3 weeks. It's already announced at the French Academy of Sciences. The English translation of that original communication in German appeared in Nature in January 23rd. And January 23rd, that same day, he made the first public presentation, not to the Kaiser, but the public presentation at the Würzburg Physical and Medical Society. That's where he then asked for another volunteer, and maybe his wife wasn't present. And so this is another famous picture, right? And that's the hand of Albert von Kolliker, who was a professor of anatomy at the university. And you recognize that this picture, whenever you see it, that it's sharper. So especially the ring looks a lot sharper than the original picture. And that's how you can recognize that this is really Kolliker's hand, and not his wife's hand. No, but you could see a pretty significant detail. Of course, he was fine-tuning the method. Within a few weeks, he could really get much sharper images already of all kinds of objects, right? And I'll show you some other examples. So these are some stamps that show, again, hands, right? Presumably Kolliker's or his wife's. Stamps from Egypt, from Brazil, Belgium, different stamps for Röntgen and his hand. Now, very importantly, the experiments were repeated within a few weeks. Campbell and Perrin in France repeated, before the end of the month, repeated those experiments. And of course, they worked. There was no magic, there was no tricks. Those will work. Before the end of the month, news reached Sydney, already there, and preliminary comments on the possible nature of X-rays, this new form of electromagnetic radiation, were already proposed by some of those 90 physicists, right? Poincaré, Thomson, J.J. Thomson, Lord Kelvin. They were already starting to speculate on the nature of X-rays, and that was, of course, a huge deal. February 14th, the English translation of that original communication appeared in Science. And it's incredible that by the end of the year, 1896, more than 1,000 scientific articles and books have been published on X-rays. 1,000 papers within a year. That doesn't happen today for anything, right? I mean, that's really, really incredible. And some of this early history of X-rays is beautifully explained in chapter 4 of this book that you may have seen. It's a really nice book. Now, here's where X-rays start sort of branching into two directions, right? One would be medical applications, and the other one would be more like structural determination or crystallography. So I'll give you a few things about medical applications of X-rays. The first time that there was a hint that X-rays could be important for medical applications came in the Lancet, January 11th. Within a couple of weeks, that's a medical journal and the British Journal of Medicine. And so they very quickly became also interested in X-rays. Specific applications to bone pathology were recorded, proposed by Lanelong before the end of the month. That's within a month after the original publication. February 23rd, there's a picture of Jones and Lodge. They reported also in the Lancet the picture of a bullet that was embedded in someone's hand. So this is the application. Somebody was hurt, and they would locate exactly where the bullet was. Well, I guess they should see the entry hole as well. But anyway, so the idea was not really to locate the bullet, but to see if there were remains, fragments of the bullet still embedded within the bone. And so Marie Curie, why do I mention Marie Curie? Not only because she's, famous and the first two Nobel Prizes in chemistry and physics, 1903 and 1911, radium and polonium. And of course she appears on many stamps, like 120 different stamps show Marie Curie. But what is important, why I mentioned Marie Curie here, is her connection to X-rays. And this is maybe not as well known as her work on radioactivity and the discovery of radium and polonium and so forth. And so she really pioneered with her daughter Irene the use of X-rays, mobile X-ray units in the field, right? And which is remarkable, because think about the First World War, 1914, 1919, and she already had 2 Nobel Prizes. She was already famous, and she was really busy, and she had a family, the whole thing, right? And she volunteered still to serve on the front with these mobile units, and to really provide a boost to the use of X-rays in diagnostics, and so that's really important. The other point I wanted to make is that the only four, then by including here Maria and her daughter Irene, in the connection to X-rays, basically I'm saying that the only 4 women who have received Nobel Prizes in chemistry had a strong connection to X-rays, which is remarkable, all 4 of them, right? Of course, Ada, Jonah, and Dorothy Hodgkin, right? We'll talk about them later. But that's remarkable that all 4 women had a connection with X-rays. This is a nice picture I found online, and it really shows how these little tracks work. And so here's the wounded soldier, and that's how they were really looking at using X-ray to see where the wounds were. It's pretty remarkable. We've heard of the Petit Curies, these tracks, and that's how it really worked. And there's a more modern. This is a South Korea souvenir sheet from 1961 that shows also a mobile truck for X-rays. This is chest X-rays for the screening for tuberculosis. It's not exactly the same, but mobile X-ray units or trucks are still used today. Anyway, so these are some stamps from various countries that show radiology applications, medical applications of X-rays. Most of these are related really to the screening for tuberculosis. So you see chest X-rays. And even Disney gets involved in X-rays. So there's, I think, Goofy, or looking at this X-ray. So that's pretty cool. And this is an incredible number that I found online. About 100 million dental X-rays are performed in the US each year. So we're talking about, say, 200 million X-rays per year in the US, not in the world, just in the US, going all the way back to Röntgen. So there has been a lot of progress. X-ray computed tomography, right, was also honored with a Nobel Prize in Physiology or Medicine, 1979, and Cormack and Hounsfield. And this is a stamp that shows a CT scan of the brain. And this is again all related to X-rays. Non-medical applications of X-rays, that's kind of what we are interested in. But before we get into crystallography as we know it, I'll show you a couple of figures. A very interesting way of how these mysterious, wonderful X-rays were promoted at some point, in the 1920s, in the 1930s. And so here's a ticket stub from an exhibit, a show that will demonstrate X-rays. And it's hard to see the fine print here, but it says, through a sheet of metal, through a block of wood, count the coins within your purse. And so all kinds of applications for X-rays. And here's one that is also pretty cool. It's how you could use X-rays in a different way. So it says here, whether stout or thin, the X-ray makes the whole world kin. That's, I think, pretty cool. This is way before Homeland Security. Right? So that's how you can look at all these potential applications of X-rays. But X-ray crystallography really, of course, you know, the diffraction of X-rays by crystals started with von Laue, and so that's part of the celebration of the centennial of the Nobel Prize in Physics in 1914. That's one of the many things we are celebrating this year. There's a number of stamps with von Laue. This is one that shows the diffraction pattern, the Laue photograph of zinc blend from East Germany, another one from Germany, Guinea-Bissau, one of those random countries to issue as well stamps for scientists. This is another weird one, not because it's from the Comoro Islands, but it shows von Laue as a mineralogist, which he was not, right? Okay, well, there he is. Anyway, the Braggs, we've all heard about the Braggs, the Nobel Prize in Physics, 1915, and for the development, for the application of really X-rays to the crystal, to the determination of crystal structures. Now, the couple of interesting things I usually like to mention about the Braggs. So first one that is still to this day, they are the only father and son team who got the Nobel Prize at the same time. There are some other father and son teams, like the Bohrs, the Bohrs, I think, the Bohrs, the Kornfeld. There are some others, mother and daughter pairs as well, of course, the Curies. But the Braggs really got the Nobel Prize at the same time for work they shared. That's incredible. Without really, that hasn't happened again. The other thing that is really that impresses students a lot is the son, William Lawrence. He really contributed. He really deserved the prize, and he shared the prize when he was only 25. He was just 25 years old, and he shared the Nobel Prize and all of that. So that's pretty incredible. This is a stamp from Sweden that shows the Braggs here. This is also reproduced in the cover of this book. It's probably the best biography of the Braggs. And lots of other stamps from different countries show the Braggs. These ones from Guinea-Bissau are interesting because they show Bragg's law. And so that's really a good example of Bragg's law on a postage stamp, and some others from different countries. The first crystal structures. And so that seminary, that first paper was from September of 1913. The Proceedings of the Royal Society of London described the structures of sodium chloride and the potassium halides, chloride, bromide, and iodide. And this is a sort of a generic view. It really doesn't matter which one is sodium or which one is chloride, of course, but this stamp from the UK celebrates the Nobel Prize for the Braggs and shows the structure of sodium chloride. And it's also incredible that in roughly 100 years, right, from the first paper, the first 4 X-ray structures, to the present, the Cambridge Structure Database contains about 700,000 structures of organic and organometallic compounds. If you add to this, of course, strictly inorganic compounds, if you add 100,000 roughly structures in the protein data bank, we're talking about close to 1 million structures right now. And that's an incredible progress for roughly a century of crystallography. That's good to keep in mind. And salt, sodium chloride, appears on a number of stamps, which I show here. That would be a separate topic on its own. Fast forward again to the double helix. Well known, the history of the discovery, the work of Watson, Crick, and Wilkins has been told many times. This is a stamp that shows again the double helix. Nobel Prize in Physiology or Medicine in 1962. And so there are, it's really important to mention at this point that Rosalind Franklin, of course, passed away 4 years before 1962. It would have been really hard to figure out who would be the 3 scientists to get the Nobel Prize in 1962. I think Watson and Crick probably would have received the Nobel Prize, whether it was Wilkins or Franklin. Of course, that's a long story. So there are no stamps that honor Rosalind Franklin. And so the closest to a tribute to Rosalind Franklin is a stamp from Sweden that shows DNA, but it shows the famous photo 51 of that B form of DNA. And so that is the photograph that she made, that she interpreted, that somehow Wilkins got hold of, and well, the rest is history, right? But that's a connection at least to Rosalind Franklin. Many other stamps show DNA. Of course, it's visually appealing. Lots of different countries show stamps with DNA. This is also really nice base pairs on postage stamps. You can see guanine and cytosine, adenine and thymine. If you look at the pairs of stamps, you look at the 3 hydrogen bonding interactions, 2 hydrogen bonds, really, really cool stamps from Macau. And Max Perutz, right? Also the Nobel Prize in Chemistry in 1962, same year as Watson, Crick, and Wilkins, right? And the first stamp honoring Perutz just was issued just a few weeks ago, March 25th, 2014. It's too bad the stamp doesn't specifically mention the International Year of Crystallography. It happens to be the centennial of his birth. In fact, the centennial of his birth was a week ago, April 19th. And so, so that's a nice stamp, first one for Max Perutz. I should also mention that this year, 1962, was incredible, right? So Watson, Crick, and Wilkins get the Nobel Prize in Physiology or Medicine. And Max Perutz gets the Nobel Prize in Chemistry. Linus Pauling gets the Nobel Prize in Peace, 1962. And Lev Landau, who really worked on superfluidity and liquid helium, got the Nobel Prize in Physics, and John Steinbeck got the Nobel Prize in Literature. So 1962 is an incredible year for Nobel Prizes. Anyway, so even though this is the first stamp for Max Perutz, a cover was prepared a couple of years before in Romania for the 50th anniversary of his Nobel Prize. And so you'll see the names of those 1962 Nobel laureates in there. That's pretty interesting. And so 2 years later, Dorothy Hodgkin, of course, got the Nobel Prize in chemistry. And the pioneer, of course, we know of protein crystallography. This is a list of some of the structure, the best known maybe: cholesterol, penicillin, vitamin B12, insulin, which was after the Nobel Prize. But a remarkable life. And she appears on this stamp from 1998, and a more recent one, 2010, which is nice about this stamp is that it really shows the electron density plot of cyanocobalamin, right? Vitamin B12, the original vitamin B12. So it's hard to see, but if you look at here the ring around the cobalt center, and it's really hard to see, but there is a diatomic unit there, and that's the cyanide group, which is easier to see maybe here. And so that's really a lot of detail into that stamp. And she appears on a couple of other stamps, Mali, Sierra Leone, still at least they are honoring her. And in the International Year of Chemistry in 2011, Israel issued these 2 stamps that show fairly complicated molecular structures, ubiquitin and the ribosome. So they appear on these stamps. Of course, the stamps were also honoring Chekhanover and Hershko, the Nobel laureates in 2004, and Ada Yonat for 2009, and their contributions to protein crystallography. These are covers signed by them, by Chekhanover and Ada Yonat, so these are related to the collection. And of course, the Nobel Prize in Chemistry in the International Year of Chemistry was given to Dan Shechtman for the discovery of quasi-crystals, quasi-crystalline materials. And he appears on this stamp from Mozambique, issued late that year, in 2011. A more recent one from Mali, and so that's a really important milestone in X-ray crystallography. And I want to show you a few stamps that portray molecular structures. Molecular structures are so important for us that I had to show you a few. And so ozone appears on the stamp. These are not necessarily X-ray structures, but these are molecular structures. There's ozone there, carbon dioxide and water, important in photosynthesis. These stamps for the International Year of Chemistry, Slovakia, and Belgium. Urea, nice representation of urea with the carbonyl group, the double bond, all the details are on that stamp. This is one of my favorite stamps because it is the X-ray structure of C60, of Buckminster fullerene, but the reason why I like it is it was printed with thermal ink. And so what that means is that when you touch the stamp, it changes color. And so what I did is hard to see here, but there's an inner circle here that is darker. When you touch it, the rest of the stamp turns white, right? So I really just touched the stamp and scanned it again. And this is supposed to be a helium atom trapped inside C60, which is really, really cool for a postage stamp. Think about getting one of these in the mail. Really, really cool stuff. All right, adamantane appears on this stamp from Czechoslovakia, 2,2-difluorobutane. I mean, that's not really an important hydrofluorocarbon. And the stamp was really celebrating the Geneva Conference, right? Organic nomenclature. And most people say that they should show 2,2-difluorobutane because the molecule had the right length. And so isoprene, right, really important, natural rubber appears on that stamp. Rubber is again a topic. There are many other stamps that show rubber. This is a good one. So Monaco. Monaco is well known for the tourism, right, for gambling. I've never been there, right? It's a nice, resort for the rich, right? But they wanted to celebrate the plastics industry, right? And which is, I'm sure, is not really important in Monaco. They make souvenirs, maybe, right? But anyway, and they show this stamp, which is a disaster, right? They show the molecular structure of methane as C4H, right? And that's and it's crazy stuff because they show methane going into this sort of meat grinder and then coming out as plastics. I mean, it's just crazy. Now, Monaco is known, of course. If I was a stamp designer in Monaco, I'd probably be in the beach, not doing my work. But so Monaco, it has made mistakes before, and so this is a stamp that shows Franklin Roosevelt, former President Roosevelt, who was a fairly well-known stamp collector. So this is based on a photograph of Roosevelt with his stamp albums and a magnifying glass, and apparently Franklin Roosevelt had 6 fingers on his left hand. So that's talk about conspiracy theories. So you can count them. This is crazy stuff. That's from Monaco. Anyway, a much more elaborate structure is a natural product, and another International Year of Chemistry stamp for this natural product isolated from the root of a tree in Indonesia. Vitamin C, nice representation of vitamin C. The Nobel Prize, of course, Tadeusz Reichstein, who was born in Poland but worked in Switzerland. Gertie Curie, so that's a nice one because 1947, Nobel Prize in Physiology or Medicine, and it's a US stamp. There are relatively few US stamps related to science, to crystallography, to chemistry, and so this is one issued in 2008. Unfortunately, it has a mistake. It shows the wrong formula for glucose phosphate. It shows the ring connected through the O3, right? I mean, it has to be through an oxygen, but it should be through this lateral to the single oxygen atom. So the mistake was pointed out to the US Postal Service, right? But the stamps were already printed. They basically said, nobody's going to know the difference. And the stamp was released like that. So all these millions of stamps show the wrong formula for glucose 1-phosphate. All right, more on the inorganic side, these Japanese stamp shows the high temperature superconductors. This is a good one also from the former Soviet Union that shows this fairly unusual dirhenium octachloride dianion. And the stamp is remarkable, of course, for many reasons. This is the molecule, of course, the anion that exhibited or presented the first example of a quadruple bond. That came in a separate paper by Cotton the following year. And of course, it's the 50th anniversary. In September, it's going to be the 50th anniversary of that paper. It's going to be a special issue of the Journal in Organic Chemistry. Anyway, what is, I think, also remarkable is that this stamp, which was first really made by Kuznetsov and Kozmin in 1963, already made it to a postage stamp 5 years later. So that's remarkable. This is a stamp that was really honoring the 50th anniversary of the Sputnikov Institute. And so that stamp was there. There was no mention, of course, of a quadruple bond, but that was really what Cotton and figured out the following year. And special down postmarks. So what is this? This is sort of like where do crystallographers go when they retire? It's kind of a subtitle for that, right? And a possibility could be the Naica mine, right? You've seen that picture, right? But that's not probably a good idea, right? Because this is 100, about 1,000 feet, below ground. It's like 130 degrees Fahrenheit, high humidity. It's not really the best place to retire, right? I mean, cool crystals and everything, right? But not really what we want. And so a much better option, I would say, is Crystal Beach. Right? Crystal Beach in Florida. There's a town in the west coast of Florida. It's called Crystal Beach. This is a cancellation from that town, and that's a pretty nice place to retire, I would say. If you want something maybe closer to New Mexico, there's a Crystal Beach also in Texas. It's in the Bolivar Peninsula near Galveston. So there's 2 crystal beaches. And if those, you don't like those, there's many others, right? There's all kinds of crystal town names on typically very small towns in the US. There's just crystal, plain crystal in North Dakota, Crystal Lake, Lake Crystal, Crystal Springs, Crystal City, Crystal Bay, Crystal Hill, Crystal Falls, Crystal River. You get the idea. So you should choose one of those for your plans. And these are typically small towns. These are the postmarks from all of those. I want to conclude by showing you an update on the International Year of Crystallography stamps. The first one really was issued in December of last year, December 3rd, 2013. It was in Israel for quasi-crystals. A stamp that is, of course, honoring Shechtman, but specifically shows these quasi-crystals. So that's a pretty cool stamp. January 30th, a stamp in India, a really nice stamp that shows the molecular structure of curcumin, the active ingredient in turmeric. And so that's pretty cool. You can even see that this is the enol form, which is not the one I show here, but that's the enol form of curcumin, which has all kinds of interesting biological properties. There's a lot of research going on curcumin. There's reviews and everything. Slovakia had a stamp issued February 14, 2014, and a pretty esoteric topic. It shows these electron density lines for this tantalum germanium tellurium alloy. So it's pretty sophisticated stuff. Nice looking stamp. 6th of March, Switzerland had a pair of stamps for the International Year of Crystallography that shows these samples of minerals, epidote and amethyst. Really nice looking stamps. And customized stamps. These are stamps that are not really officially released by a postal service, but by an individual or an organization. And typically they are valid for postage, so they are made with the blessing of the postal authority. So these are 4 stamps from Moldova for the International Year of Crystallography. I've seen some of these on some of the posters that are publicized in the International Union of Crystallography and the International Year of Crystallography. And similarly, these 4 were issued a few weeks ago in Poland that also celebrate the International Year of Crystallography. These were prepared by the Polish Synchrotron Radiation Society. So they are out there. I want to really conclude by telling you that there is a group of people that collect stamps related to chemistry and physics. I'm not the only one. But so we have a website with all kinds of information and articles and pictures and everything. We published a magazine called Filatelia Chimica et Physica, all kinds of articles related to chemistry and physics, and occasionally including crystallography. I write regularly for Chemistry International, the IUPAC news magazine, every couple of months, short article with this. And the 4 articles I've written so far this year are related to crystals and crystallography. So, and that's freely available on the web, which is Chemistry International. And last but not least, I want to include a few acknowledgements. I want to thank my research group. The research group, of course, I need to thank because it's their effort and their independence that allow me to have this distraction of investing some time during the day searching on eBay for stamps. So I couldn't do that without their maybe unknown effort. But that is true, so they deserve to be credited. I'd like to also thank for the same reason my family. Because again, long nights of eBaying at home, and they know, now they know why. And I wanted to also thank what I call the crystallographers in my life, right? And starting with Arne Reingold, I think some of you, many of you may know Arne Reingold. He has been really the crystallographer, the colleague who really inspired me to appreciate crystallography in all my independent career. I've known Arne for about 20 years now, and so he has been a blessing to my career. I've collected through collaborators lots of X-ray structures. Here I'm listing a number of what I call alumni from Arne Reingold University, and including Ilya, who is here in the audience. Thanks for the lottery ticket. And this is an interesting picture of Arne right before he moved from Delaware to San Diego. And I found this sign that says X-Ray Boulevard on eBay, of course. And I sent it to him, and he still has this sign hanging in his lab in UC San Diego right now. Other individuals, some of which you also know, have helped us a lot over the years with X-ray crystallography. So I'm not really a crystallographer myself, but it's a wonderful technique, and I have really an appreciation for the technique. And this is the last slide. I wanted to mention my email address, because if you're interested in any images that I showed you today, I would be more than happy to email any of these images to you. These are all in my collection, JPEGs, it's all free, it's really easy to do. With that, I just want to thank all of you for coming early this morning. Thank you very much.